Okay, welcome to note set number 19, where we're going to dive into some of the details of the DFT. So if you remember from the last note set, we were striving to get a way to compute and view the DTFT of some collected signal, connect that DTFT back to the CTFT, which we can do through sampling theorem, and we ended up with this kind of developed tool called the DFT that has some very precise machinery built into it, so it works in a very precise and desirable way from a mathematical point of view, but also provides us with a way through zero padding and such to actually compute points on the DTFT of some finite duration chunk of signal. And if we do all that correctly, we can hopefully get a pretty good view of what the CTFT of the original continuous time signal looks like. So we set this up in a very formalized way so that we would get certain properties, and now we're going to start looking at some of those properties. Knowledge of these properties are essential for understanding how to use the DFT in various applications besides just using it to compute and view something that should show you what the spectral content of a signal looks like. Okay, so let's to the next slide here, where we just reiterate our definitions of the DFT and the inverse DFT. So the key here, you'll notice that I'm switching some notations around. I'm talking here about little omega k, so I'm switching to Proachus and Monolakis's notation rather than what I've used in my signals and systems class with a uppercase omega. But nonetheless, we see that we're operating at a spacing of 2 pi over capital N, where N is the number of data points that we put in, and we're not really saying whether some of those are zero padded or not. So however many samples we got, with or without zero padding that's going into the DFT, that tells us what our spacing is. So we put n x of n samples in, we compute this quantity for n different k values, so we have n entities mapping to n entities. And then we can undo that. So if you give me n DFT points, I can take those and put them into this formula here and undo the action of the DFT. And we'll see some applications along the way as to why we would want to do that. In fact, we'll start to see some of that in this set of notes and then in subsequent sets of notes. So this is just for nailing down notation and reiterating what we mean by a DFT and an inverse DFT. So one of the things that is often useful to be able to do is to interpret this DFT operation as a matrix operation. So I don't know if you've had some sort of linear algebra in the past, but if you have, this will provide some useful insights. If you haven't, don't get too worried about it. It's just another way of thinking about the idea of computing a DFT and an inverse DFT for that matter. So we have up here at the top our definition of the equation that defines the DFT. So we've got a sum here that for each value of k that we're allowed to pick, we do the summation and we compute each one of the different DFT coefficients is what we say. So if we look at this and write out kind of what the summation looks like for each value of k, we can start to see kind of a structure here. And So for x of 0, we see that we have x, little x of 0, x of plus x of 1, adding up all the way out to x of n minus 1. Then for DFT point at k equal to 1, we see that we're taking all of our sample values. Oops, that should be minus 1. We see all of our sample values going all the way out to, times complex exponential at all the different values of this thing evaluated at different values of n for the given value of k equal to 1. So revisiting this top one, when we set k equal to 0, we get e to the j0, which is 1, so that's why we just get the samples there. Now we go to k equal to 1, we get e to the minus j. Let me see if I can get rid of some of this stuff here. We get e to the minus j 2 pi, now k is equal to 1, so 2 pi n over capital N. So we get 1 times n there. So we're going to get 1 times 0 here, 1 times 1, all the way out to 1 times n minus 1. And so that's what we have for that one, and then all the way down to the bottom one, and again this should be n minus 1. Same kind of thing, except now we're evaluating this at k equal to n minus 1. So we get x of 0 with n equal to 0, x of 1 times this thing with n equal to 1, and so on and so on and so on. So if you look at all of this carefully, you can see that there's a fairly nice structure here. So if we form a matrix here where each row is a complex exponential of a certain frequency, and yep, I missed a negative sign here on all of this, so there should be a negative sign out in front of each one of those. So we've got each row is nothing more than one of these things with evaluated at k. So the top row is, well, let me say it this way. The top row is the e to the minus j 2kn evaluated for k equal to 0, and then as we sweep across, we're going to the different values of n. Then the next row down is for k equal to 1, and n going from 0 to n minus 1, and so on. All the way down to the last row is k equal to n minus 1, with little n sweeping from 0 to n minus 1. And we see that the structure tells us that we take each one of these and multiply it by the element in the first column for the corresponding row. So if I want to compute, let me get rid of some of this stuff here. Let me do it this way. So if I want to compute, say, x of 1, I'm going to take x of 0 times a 1. I'm going to take x of 1 times e to the minus j 2 pi 1 times 1 over n, and so on, all the way down to x of n minus 1 times this thing with a negative sign on the j, and so on. So each, so the kth one of these is this element by element multiplied by the elements along the appropriate row. And so that's just standard matrix times vector multiplication. So once we have this idea, we can then very easily rewrite this DFT matrix in this form. And we've used this common definition, this common symbol, W sub n. So whenever you see that showing up in a DSP book, it means this thing, e to the minus j 2 pi over n. And that's actually just taking the nth root of, well, it's called the nth root of unity, and it's basically finding the nth, well, it's all the solutions of, say, x to the n plus 1 is equal to 0. So anyway, it plays the role, just an easier notation for writing out those complex exponentials, that's all. So DFT matrix here is no different than before, and we define this little x matrix or vector as the signal samples, and this capital X vector as the DFT points. And then here's the beauty of this. Since we have an n by n matrix, and we can actually establish that that matrix is invertible, we can find its inverse. And so the inverse is the matrix that gets us back to where we started. So if we take the inverse matrix, multiply it by the DFT vector, we get back the original signal vector. And it's pretty easy to verify that the inverse of the DFT matrix is just a 1 over n times the complex conjugate transpose. So this W star, you transpose the matrix. So imagine drawing a line down the diagonal and then holding on to this corner and flipping it along that line. So now this becomes the first column, this becomes the second column. So you flip it, and then you also have to complex conjugate it. But if you look at this thing, you'll see that it's, well, yeah, it's got a certain amount of symmetry, so that's why this actually happens the way that it does. And it's because of the similarities here between those factors for both DFT and IDFT. So really all we need to do is, we don't even really need to flip it, we just need to complex conjugate it. So it's very easy to get the inverse matrix. You don't have to really do anything at all other than take complex conjugate. So that's just an aside, not a big deal, but just something I thought should be mentioned as we go through this. Okay, some properties of the DFT. You've learned properties of CTFT and DTFT and Z transform and Laplace transform, and some of those properties will carry right over. So the big one is linearity. So all of these transforms are linear transforms. So if I've got some little x1 and I know it transforms to big X1, and little x2 transforms to big X2, then any linear combination of little x1 and little x2 will result in a transform that is the same linear combination applied to big X1 and big X2. So that's kind of the result, and it's used all the time. Periodicity. We know that since the DFT ends up being points on some DTFT, and we know that since it's a DTFT, it's periodic, we can easily see that the points for the DFT are also periodic. So that's a very easy result to see. The other thing is, and this is a little harder to see, once we compute the DFT of something and then we invert it with the IDFT, we need to, at least mathematically, interpret that process as creating something that is periodic in and of itself. And we'll see what we mean by that as we go through this. But for now, let's just prove this periodicity in the time domain due to computing a DFT and then taking its inverse DFT. So we start off here with just writing out the DFT, inverse DFT result for a shifted version of x of n. So I start off with a regular DFT, inverse DFT result, and we're used to seeing if I had just an n here, I would have just an n here. But because I have n plus capital N, I will have n plus capital N there. So this is just replacing capital, or little n by capital. Little n by n plus capital N is what we're saying there. So we know that this is true. We've just made a substitution. Then we break this complex exponential down into two parts. So here's the one part, here's the other part. And we notice something about that first thing. If we cancel the capital N from each, we end up with e to the plus j 2 pi little n. So that's a complex number that lies at 0, angle of 0, angle of 2 pi, angle of 4 pi, angle of 6 pi. So all of those numbers are the real number 1. So we can replace that by 1. And this part, for now, just stays there. And so this part is gone. And we see that what we have is just the regular IDFT. And so that gets us back x of n. So what that shows to us is that when we're doing DFT processing and we do an inverse DFT, we need to interpret the result as having the potential of being periodic. And what I mean by potential of being periodic, I'll illustrate on the next couple slides. So this is a little bit of a subtle view here, because really we're taking n samples, we put them into the DFT, we get n DFT points, we put those into the IDFT, and we get n points back. So what does it mean for those n points to be periodic? So all that really means is, well, we'll see it on the next slide. So here's what we're saying is that we start with some x of n, which may not be finite, and we grab some n samples. So there's the chunk that we're going to grab. And so now here's our collection of finite number of samples that we're going to take the DFT of. We compute the DFT and we get this. Now we're going to, we have the real part and we have the imaginary part. Now we're going to take this, we take the inverse DFT of that, and what we get back is exactly what we started with, but there are these vestiges, or these little ghosts sitting out there. They're not really there because we've only computed what's inside this box, but they are mathematically there. They are waiting to pop into view if you were to do something to uncover them. And we'll see what that means in just a little bit. So, this periodic aspect, or these periodic vestiges of the signal, they arise only in the context of having computed a DFT and then doing the inverse DFT of it. And we can kind of think about it in the following way. So we'll say that this x of n here is some L point signal segment, and we're going to define an n periodic signal by taking that little segment and shifting it by integer multiples of n, and then adding them all up. So this periodic result comes from taking the DFT of the original signal, finite duration, doing the inverse DFT of that, and we can imagine that being this periodic signal. Even though we're only getting back from our computer n samples, we can interpret those n samples as being one period of a periodic signal. And tied into this idea is this idea of a circular shift, and we're getting to the point where we'll be able to see why we have to fuss about all this. So suppose I have some finite duration chunk of signal. I'm not even defining what it is outside. I'm not saying it's equal to 0. I'm just saying there's my finite duration chunk. And then here is my periodically extended version of that. Now suppose I wanted to shift that periodic signal by 2 samples. So one thing that we can see is this idea that when we shift that, we are shifting to the right by 2 samples. So this one goes over to here, this goes over to here, and so on. But notice that we've also shifted in 2 samples from outside our original range. And so that's the idea of starting with a finite duration signal. Imagine periodizing it. Imagine shifting that periodized version and then grabbing the range that we originally looked at. So that's one way to look at it. And another way to look at it is that we can think about arranging our samples around a circle. So since we have 4 samples to begin with, we start with 4 samples arranged around a circle, so they're at 90-degree spacings. If we had more samples, we would have narrower spacing. And we start with x0 here on the right-hand side, then x1, then x2, and then x3. And over here we're talking about circularly shifting that. So if we are circularly shifting this by 2, like we did up here, we would be shifting the 3 element in. So this gets shifted all the way over to there, and you can see that the 3 now resides there. And so you can just barely make it out. This is an x tilde that we're talking about here. And so that's one way to visualize this idea of a circular shift. And so you're probably at this point saying, I don't get why we care about this. Well, you can't get it yet. We're getting there. So bear with me. So for notational purposes, this circular shift can be written using modular notation. So if we rewrite n minus k mod n, that actually does this kind of idea. So if we just look at our original n in this column, and then we look at our mod 4 version of that, we see that nothing happens from here up to there. But then over here, when I get to 4, I would be jumping back to 0. So this is like going around the circle. I'm going 0, 1, 2, 3, 0, 1, 2, 3, and so on. So that's what this mod representation looks like. So you should be able to convince yourself that doing the regular index substitution n minus k, but then slapping on a mod n will do the same thing as what we just defined as a circular shift. And this double bracket notation is just a convenient way of notating this idea of mod n. Okay, on this slide we're going to talk about the circular shift property of the DFT itself. So this comes from the shift property of the DTFT, and so that's exactly the same same kind of idea that we had for the DTFT. So to just remember that, if we took a signal y of n and defined it to be the regular time shift, shifting by L some signal x, the effect in the frequency domain is just this linear phase term. So that's a fundamental idea in discrete time signals and systems that we've talked about before. Now for the DFT, we have a similar property, but it's for a circular time shift rather than a regular time shift. And so instead of having, like we have up here, a regular time shift where the whole signal shifts left or right, we have here the modular shift or circular shift. And remember this, when we're dealing with DFT, we're talking about a chunk of signal. And so these, when we shift this by L samples, it's going to circle around and come back in the other side. That's what we talked about with a circular shift. And so we get this result that says if we shift in the time domain circularly, then in the frequency domain, the new signal's DFT has a linear phase term, and you can compare the linear phase terms, and you can see that here we had omega as our variable. Down here, our frequencies are controlled by k, spacing of 2 pi over n, and so you can see that we have the 2 pi k over n playing the role of omega, multiplying the L that we have just like up here. So it's remarkably similar going on in the frequency domain. So in fact this is a linear phase shift, literally. So another way to think about this is to say, what if we apply a linear phase shift in the frequency domain to a DTFT, the effect in the time domain is a regular time shift. But if we apply a linear phase shift to a DFT, the result is a circular time shift. And remember, this kind of has to be because we're talking about the DFT being the inverse DFT giving us a chunk of data. So what would that mean to be time shifted regularly? We have to have some idea of a time shift, but in order for everything to be consistent, it is a circular time shift. And in fact, it comes right out of the math that way as well. So I know these are funky ideas, but if you can nail these down, then you have a good feeling for how the DFT works. So basically, these two things are saying the same thing, just depending on which view you're thinking about, the action happens. So number one says if you circularly shift in the time domain, that it corresponds to applying a linear phase term to the DFT. Number two says if you've got a DFT and you impart a linear phase shift to it, then you do the inverse DFT, you'll get a circular shift imparted to it. So what that says is that if you think you're going to make a regular time shift by taking the DFT of something and then applying a linear phase shift and then shifting it back, you'll be surprised. So anyway, one peculiarities here. Now to prove this, we'll prove this one way, which is kind of a more obvious way to prove it, and then we'll prove it a more step-by-step way. So we know that when we do the inverse DFT of something, we can think about the result as being a periodic and extension, and so this is just a mathematical characterization. Again, remember, when we physically do the IDFT, we just get back n samples. We get one of we get the fundamental cycle or period of this x sub p back. But when we use this little trick, it helps us see what ends up happening when we do other things. So here, this statement is kind of doesn't really have much meat to it, right? We could just as easily leave off the periodic part of it. But let's see what happens if we start with our DFT, we apply a linear phase term to it, and then we take the inverse DFT of that. So we can just plug in this thing inside the summation for a DFT. So there we have it there. Clear some of this stuff off here. And so now we're going to combine this exponential with this exponential, and so we get something that looks like this. So we have a j, positive j with an n and a negative j with an l. Everything else being the same, so that's how we get the n minus l there. And now we look carefully at this. This is nothing more than the inverse DFT of this thing, but normally where we would have the n showing up, we've got an n minus l showing up. So this is the periodic signal shifted by l, and that is nothing more than a circular time shift. So that's one way to view this. And let's look at what the book did, a little more step-by-step proof. Works out exactly the same, but it's a lot more complicated than using the tricks that I just used. So they're going to start and prove it in the other direction. Notice that what we did was we applied a linear phase and then saw what happened. They're going to apply a circular time shift and see what happens to the DFT. So this is just by definition here. And this little box up here is just pointing out that for only certain values over the sum do you actually have any need for that mod. So so we'll break it down into the parts where we need the mod and the parts where we don't need the mod. So when n is bigger than or equal to L, we don't need the mod, and so that's that range of the sum. And then down here, we do need the mod. And so when we do need the mod, we can rewrite this way. We couldn't just rewrite this way directly because there are places where it doesn't hold. So so now we've got this replaced here. We've got this just going straight down there. And so now all we're going to do is do a change of variables. Let me clear some of this stuff off here. So if we do a change of variables in each of the sums, so this one we're going to just change so that instead of going from L to n minus 1, we're going to go from m equals 0 up to n minus 1 minus L. in other words, we're going to let m be equal to n minus L. And so that's how that one changes. Over here, we're going to let m be equal to n minus L plus n. Then we get, when we make those changes, we get this change here, we get this change, and we get a change in the range of our summation. Now, let's clear some of this stuff off. Once we have that, we re-look at what we've got. Look at the summand of both sums is exactly the same. And notice that we've got from 0 up to n minus 1 minus L. And notice that this just picks up on the very next highest sample and goes up to n minus 1. And so this is just two summations that are over contiguous regions. And so we can combine those together. And when we do combine them together, we've got kind of a common exponential term here that can be factored out. So we factor that out in front. And this is just the DFT of the original signal. And so that goes there, and we're left with this linear phase term out in front. So a very simple proof on the previous page showing going from applying the phase result to getting the circular shift. Here we're doing a little more complicated proof, starting with the circular shift and going to the linear phase result. Now they did not take advantage of writing out the mod as thinking of it as a periodic extension. So sometimes that's helpful, and so that comparing these two approaches shows that sometimes the mod is helpful and sometimes the periodic extension viewpoint is helpful. Okay, so let's look at another property that has to do with the circular nature of the DFT, but this is the circular nature in the frequency domain. So we know that the DFT itself has a periodic nature, and so if we frequency shift the signal, so if we start with some x of n and we multiply it by a complex exponential, so remember this form written out just as e to the j 2 pi nm over n. So we are modulating with a complex exponential as a function of n time. So our frequency is 2 pi m over n. So notice that our frequency here is has the value equal to one of the DFT frequencies. So we can't just pick any old frequency that we're modulating by, but we're modulating by some integer multiple of our DFT frequency spacing. So basically, if you think about it, what we're really doing is shifting the underlying DTFT by an amount that keeps everything, all the points kind of on the grid. So it makes complete sense that we would be shifting, just shifting the DFT points around as they go along frequency. So we can write that either using the double bracket notation, or we can write it with the mod n notation. So basically it says if we modulate the signal, and again we're talking about a signal segment, so this x is just a little block of our signal, by a frequency equal to one of the discrete frequencies of the DFT, then the corresponding DFT has a circular shift imparted to it. So that's one view of it, and this is the dual view of it. If we create a DFT and then we circularly shift it and then do an inverse DFT, that imparts a modulation on the signal. So what we're really seeing here, the fact that it's a circular shift, is really the same as for the DTFT. The only difference here is that this result holds for the DFT only for one of the discrete frequencies defined for the DFT. So that's the key distinction. And then finally we get to kind of the most important property of all Fourier transform properties, the convolution property. So for the regular CTFT and DTFT, we had the convolution property said that if we convolve in the time domain, that corresponds to multiplication in the frequency domain. So this result for CTFT and DTFT allows us to say, hey, systems really do convolution, theoretically, but instead of analyzing them in terms of convolution, we can more easily analyze them over in the frequency domain in terms of multiplication. Now, because of the circular properties of the DFT and the IDFT, we have to modify this result for when we try to do a version of it for the DFT. So when we multiply two DFTs and then take the inverse DFT to get back to the time domain, what we get is not a regular convolution. It's something called a circular convolution, and we'll see more precisely what that looks like in the next several slides. But for right now, just keep in mind that that little symbol there, which is different from what the book uses, and later I'll use yet another symbol that I had embedded in some other notes. But basically we're saying that x1 of n is a length n signal, x2 of n is a length n chunk of signal, and we are doing this operation called circularly convolving them relative to the length n. And so unlike up here, where convolution is the thing that we really are interested in analyzing, so we say, well, systems do convolution, so we can analyze the action of the system in the frequency domain. Circular convolution is by no means something that we usually want. In fact, I can think of just one place that I've ever run up against a scenario where I really wanted circular convolution, but that was just because of some idiosyncratic nature of what it was, what the scenario is in that case. So we'll see later on how to trick this procedure into giving us the kind of convolution that we would really want. So basically we're answering the question, if we multiply two DFTs together, take the inverse DFT, we're showing that the result is really not what we would perhaps expect, regular convolution between those two signals. And we'll see that later on that we'll be able to, like I said, modify this so that it will, or trick it up so that we can make it do what we want. And what we'll actually be able to do then is actually implement systems in the frequency domain. So we would treat one of these DFTs as the DFT of some input signal. We would treat the other DFT as the DFT of some impulse response. We then form the product between them, and then take the inverse DFT of that product, and as it stands right now, we would get circular convolution between an input signal and an impulse response. We don't want the circular nature, but we'll see later with some clever zero padding, we can make this work the way that we want it to, and we can actually implement a discrete time filter in the frequency domain. And right now, you may not really see any real advantage to doing that, but later we'll see that there is an advantage to doing that. So right now, just take this as a stupid DFT trick that doesn't quite give us what we want. So, a lot of the theory that was developed for DFTs was pretty much just struggles trying to make it work the way that the researchers really were hoping that it would work. Okay, so let's move on to the next slide. So before we really introduce what circular convolution is, we'll actually prove this. Now you might be saying, how can we prove this if we don't know what circular convolution is? Well, we're going to do basically what the early researchers did. They said, aha, what would happen if I multiplied two DFTs together and then took the inverse DFT? And they were hoping that it would give convolution. And what they found by going through steps similar to what we'll go through here is that, well, not quite. It gives this other thing, and they interpreted it as a circular version of convolution, and so that's what they named it. So we're going to prove this here by starting with that basic line of questioning. What if I have two DFTs, I multiply them together, and I take their inverse DFT? What do I get? So we'll start off for m equal to 1 and 2. So we'll have x of 1, DFT, DFT sub 2. So it's just defined as regular DFTs for two different signals. And then we form a third DFT by just multiplying those two original DFTs together. And then we say, let there be some signal x3 in the time domain that comes from doing an inverse DFT of this new DFT which was formed by a product. Okay, since it was formed by a product, let's stick the two explicit symbols in there for each of them. And now this next step is very important to understand why we do it the way we do it here. So let me get rid of some of this stuff here. The trick is that I've got two different DFTs in here, each defined in terms of a sum. And we typically use n as the variable over which we are summing. Now, anytime you integrate, anytime you sum, those are just dummy variables. And we can literally change them to any symbol that we want without changing the result, because it's just a name that we're using to keep track of our counting through our summation. And so what we want is the sum for this one to be not linked at all to the sum from this one, because they're not. They're two separate things. The indexing of one sum should not interact with the indexing of the other. So if we put them both in with indexed by n, then we will get confused and inadvertently link elements from one sum together with the other one. So that's why down here in this square bracket we have replaced for the first DFT, and you can see that we've replaced the n by m. And for the second one, we've replaced the n by l. Once we do that, now we are free of the risk of linking those two sums together. I can see that this term belongs to that sum, this term belongs to that one. This exponential is indexed by m, this one is indexed by l. But we do see a legitimate linking between those two exponentials. They are both linked by the value of k, but that's okay, pun intended there, because they are both being evaluated at the point k. Okay, so we now have the sums properly inserted, and they're finite sums, so we can move them around pretty much however we want without running any risk of convergence issues and things like that. So what we're going to do is reorder these sums, and I would encourage you to play around with a few actual sums, short ones. Sum 3 terms together times the sum of 3 terms together, and keep track of how the products of those things work, to kind of play around with this and be sure that you can interchange these things. But basically we can interchange and group these things however we want. What we should always strive to do is keep this, any term that corresponds to the index of a sum to the right of that summation. So you can see that my m summation is out in front, so I can bring this m term all the way out to that, but no further to the left. And notice that I have another m over there. Likewise, I have L sum there, so I can pull this L term all the way out to there, and I have an L dependence there. But anything that has this K dependence here cannot be pulled any further to the left of that. So getting the right ordering of the summations is kind of crucial to where you're going to end up going. But in this case, what we're trying to do is get all of these 3 exponential terms together, and you can see that they all have a k in them. They all have a 2 pi over n. So the key difference between them is the m, the L, and the n. And you can see that we've got a negative sign, a negative sign, and a positive sign. So we can put them all there, accounting for the negative signs. This is just properties of combining products of exponentials. And so we now focus on this inside sum here, and we need to figure out what that thing's going to look like. So let's have just a little aside to find out what that is. So a general result here, summing up a bunch of exponentials of the form that we have, we can show that that's equal to n whenever capital N, whenever little n is equal to some integer times capital N, and it's equal to 0 otherwise. So the result that we're going to get will depend upon the specific value of little n, how it relates to big N. Okay, so that's the result. We can express this a little bit more succinctly by saying it's a delta function that is periodic with a period of capital N. So really this thing is like the impulse train that we've seen a couple times previously in this course already. So let's see if we can establish this result. So first of all, for k equal to 0, we would be up at this point. That's a pretty obvious result. When we plug in k equal to 0, the e to the j thing becomes 1, and we're adding up n1, so obviously we get n. When we have little n is equal to capital N, then we'll have the k, which is now n, cancel with n, and I have e to the j 2 pi n. So each one of those is just some complex number whose magnitude is 1 and whose angle is 2 pi. So if we look down here, we're basically just adding up a bunch of elements that are all lying on the real axis. So I show them tip to tail down here just to show how they add up. And in that case, we have 4 of them, so capital N is equal to 4. That will hold true for any integer k, because for any integer k, the thing that I have here is just going to be e to the j 2 pi k, just e to the j 2 pi, well, I've done it here. This should be some other, not this k is not this k. Just some other integer. Let's call it p for now. So I would end up with e to the j 2 pi kp, which again is just a complex number with an angle that's an integer multiple of 2 pi. So we would still end up with this scenario. Now, the interesting thing is for the other case, when little n is not some integer multiple of big N, we can prove it this way, which just uses the geometric sum result. So we write this out this way and then use a specific result for the finite sum of any number a to the k, and we can get that result, and then we just manipulate it and show that it's equal to 0. Or we can say, look, I'm summing up a bunch of complex numbers, and if you look carefully, when n is not an integer multiple of n, what I'm doing is adding up a bunch of complex numbers that are all the same length, 1, but are equally spaced in angle. And so if you think about those as forces, all acting on the center point, because they're all equally spaced in angle, the total force cancels out. So we end up with 0. So we can establish this result pretty straightforwardly a variety of different ways, either with just pure math or looking at things more graphically, which hopefully by now you've realized that's one of the things that I like to do. I love doing the math, but I also like to look carefully at, what does it really mean? How can I visualize this? So we now have a result for this. Even though we have something a little more complicated here, when it was just n, we had delta of n here, modulo capital N. Now we've got n minus m minus l, so we've got delta of n minus m minus l modulo n. So we can substitute that in. And so now we get this delta function substituted in, and now we're going to have kind of a sifting property happening here, but it's a sifting property that is kind of got a periodic nature, so it's got a mod n characteristic to it. So we have to realize that as we we're summing over L, so as n minus m goes to even bigger numbers, some integer multiple of L, this thing, the mod, will end up bringing it back inside the point where delta will spike up to be equal to 1. So if we account for that mod nature, we can end up getting this result down here. So it's going to sift x2 at the point n minus m, but evaluated mod capital N. So that's the distinction. And if you're unclear as to why that works, just take a specific example. Take a specific capital N and think about what that sum is doing modulo n. And so what we finally get is this result that says that the signal that we get after we form two DFTs, form their product, take the inverse DFT, ends up looking like a convolution, except one of the signals, the signal that is flipped and shifted, its indices are, after flipping and shifting, are evaluated mod n. And so that's what we actually define to be circular convolution. So it's not quite the normal convolution, it's a variation on that, and as I've said already, we don't really want this. So if we put ourselves in the shoes of the original researchers, at this point we might feel a little bit of disappointment. Oh crap, it doesn't give me what I want. But then later we'll see that as a good researcher we don't necessarily give up. We explore and we then say, okay, can I fix this? Can I still put this to use? So this is how we define circular convolution, and we'll see a little bit more about that in the subsequent slides. So part of the process of doing this circular convolution involves reversal, so that's the flip that we're used to, and shifting. So we should look at how reversal and flipping works when we've got the mod n behavior involved. So if we just look at some x of n going from 0 down to 7, and so we look at that, and then we look at this x of n minus n here, we see that this is just going 0, and then we're working our way backwards through the function. So the 0 stays fixed, but then instead of going in this direction, we're actually going down here and working back this way. So it is kind of a reversal. I'm illustrating it up here. There's x of n, and then what I would do is put this one first, then this one, then this one, and so on, and so on, and so on. So let's see another way of thinking about this. If we take our signal samples and put them around a circle, and this is kind of why we call this circular reversal. So if we put them around the circle with forward being counterclockwise, so we've got 0, 1, 2, 3, 4, 5, 6, 7. So if we've got all those, and then we can think about going in reverse. So this is exactly like what we think about for just time reversal on a linear axis. Now we're going to do time reversal on a circular axis. So we start here, instead of going in this direction, we're going to go in this direction, but we start at the same place. So we go 0, 7, 6, 5, 4, 3, 2, 1. So here is our x of n in the correct order, and then here is the reversal of that. So basically I just write in the counterclockwise order the order that I would get going in clockwise on the original. So you can see that if I go clockwise here, I'll go 0, 7, 6. So I've got 0, 7, 6, and so on. So that matches up with what we have here. And notice that things stay in place, so they don't really kind of move. They don't flip, so to speak. So it's not like all of this gets moved over here. It just stays in place, but is run backwards in some sense. So I know it's weird, but with a little bit of thought, you can nail it down and have a better feeling. So with that in mind, we can think about circular convolution in terms of this circular axis view. So up here on the top half, which we've labeled A, we've got x1 of n, and it's going x1 of 0, of 1, of 2, of 3. And we've got some actual numerical values to help us visualize this. So x of 0 is 2, x of 1 is 1, x of 2 is 2, x of 3 is 1. Then over here we have the other signal, and it's also going index 0 of 1, of 2, of 3 in the counterclock direction. And to give it some specific values, it's going 1, 2, 3, 4. And so what we would like to do is circularly convolve these two length 4 finite duration signal chunks. And so we now have the machinery to do that. So we've got this thing here. This is our equation for circular convolution. So x2 has to be flipped and shifted with the mod n behavior. So remember, it's the putting it on the circle that gives us the mod n behavior. So, so leaving x1 by itself, and then taking this x2 and first flipping it, because remember when we did regular convolution, we would first flip and then shift that flipped version. So this says, think of it as a function of that's been flipped, and so now we're going to just flip this thing, and so it's going to go x2 of 0 stays, and then we're going to go counterclockwise on this curve, on this circle, but we're going to read them off in this order over there. So so we'll go, we'll have the 4, we'll have the 4, the 3, and the 2. And then, just like we have for regular convolution, we need to multiply these two things together for each different shift. So here's the flipped one, and we're going to look at the product for a shift of 0. So I don't like what the book has done here. This really I would call of minus m to match up with this minus m. This figure is from the textbook. And so what we're going to do for n equal to 0, that means that we don't do any shift at all. So we're going to take these numbers times these numbers, and when we do that, we get these, and then we're going to add them all up. So we get a 2, a 4, a 6, and a 2 added up, and we get 14. So the 0th output of this circular convolution turns out to be 14. Okay, go to the slide. We're now going to do the same thing, except now evaluate it for n equal to 1. So we now have the original functions up here, and now we have this thing reversed but shifted by 1. So remember, reversed gave us we would have a 1, a 4, a 3, and a 2 going in this direction. But what we've done is shifted, so we've laid them out in that direction, and then we've shifted them 1 clockwise. So we had, I'm sorry, we shift them 1 counterclockwise. Once we shift that counterclockwise, we then do the multiplication. We get these values, we add them up, and that's our result. And you can, so we now have 2 values for the output of this circular convolution. And the book does 2 more examples for n equal to 2 and n equal to 3. And then notice what happens. When we get n equal to 4, we are shifted all the way right back to our starting position. Unlike linear convolution or regular convolution, circular convolution of 2 sequences of length n will end up with only n unique values. Keep that in mind as you think about that. So that's why we really only need to do 2 more of these to complete the example, and the textbook does those for you. But what I do is show you a different way. You know, there are times I like that circular viewpoint, but I find it to be more often confusing than helpful. There's a few times where it's helpful, but as you've seen, I kind of resort to a periodized view of all of this rather than this circular view. And you can do either one, but I just find the periodized view to be easier to wrangle with and easier to see, to be honest. So here's what we're going to do. Here's our original signals. Remember, all this circular convolution deals with finite chunks of signals. So we're going to stick with our n equal to 4. So there's our 4 original samples, same as our original example. We had, let me see if I can do this here. Yeah. So we have our our 2, our 1, our 2, and our 1. And then we have our 1, our 2. See, the problem when I do this, you can't see what I'm doing. When I make that, it's that little symbol, that arrow symbol, is now completely under my finger, so I can't see where it is. So I'm going to not do that unless there's, what is this one? Let's see what that one does. Okay, lightsaber. I like the lightsaber. So this goes 1, 2, 3, and 4. I like the little sound too. So I could play with this all night. And then this goes 2, 1, 2, and 1. So this is exactly like we had before. What other options do I have for that? All right. Well, I guess we'll stick with that lightsaber, even though it makes a little noise, but it sure is fun. Okay, so there's the 2 chunks that we want to do a circular convolution for, and here are the rules for doing circular convolution my way, using the periodized view of it. So the first thing you do is you periodize your original signal. So they both have to be the same length. And later we'll say, well, if they aren't, we'll zero pad the smallest one up to the largest one. But for right now, we're assuming that both signals that we are to circularly convolve are the same length. So, so there's our originals, and then we periodize them. So we just create a periodic version of them. Okay, so we've done that. And the next step then, let me try to get rid of this stuff here, which I can't now. Let me get rid of it this way. Okay. All right, so we're back with that. And so we've periodized them. And then, so here was our origin right here. And so we are to flip about the n equal to 0 point. And so down, but we only need to flip 1. So remember, just like regular convolution, we leave 1 and we flip 1. So let's flip. Which one do I flip? Let's flip the bottom one. So we are going to flip that. So if we take this, I anchor it at this point and I flip. And so you can see I keep that. And once I flip, notice that these red ones end up over here, but in reversed order. And so there they are. And so this is just the same exact thing that you get. You can check. The same exact thing you get with that circle view. It's just that now it's a little easier to see what we're really doing. And also, I mean, flipping now is exactly the same as flipping before. We're just flipping a periodized version of it. So that's why I really like this periodized version rather than that circular version. Okay, so we've got the periodized version flipped. And so now to find each one of our outputs, we, just like before, we just need to shift. So to find the n equal to 0 output, there's no shift since the amount of shift is equal to 0. So we just flip and leave it, and we sum over 1 cycle. So here's our 1 cycle. We just sum over that. So we'll sum up those 4 products. And that's our output value for that n equal to 0 out. And if we just continue with, here are all 4 output, well, the remaining 3 outputs. So we have for n equal to 1, I've flipped and now I've shifted to the right, just like before for regular convolution. I've shifted to the right, and I now sum up these 4 elements. And I get a number, and that's my output signal at n equal to 1. Now I shift 1 more to the right, So you can see that I've shifted the bottom one to the right, and I'm going to sum up over one cycle, and I'll get a number. I sum up the product over one cycle, and I get a number, and that's my output sample at n equal to 2. I do one final shift for n equal to 3. That's a total of 3 shifts from the original flip. I sum over one cycle, and I get a number, and that's my output sample at n equal to 3. Now notice what would happen if I shift one more. Go back to the previous slide, and you'll compare it to the n equal to 0 case, and I'm right back where I started. So it's also much easier to see that there's only n explicit unique values from this circular convolution. So you give me 2 length n chunks. I can circularly convolve them now using this periodized viewpoint, and I can create n output samples. Remember, and maybe go back and revisit, think about these 2 signals as continuing finite duration signals with zeros before and zeros after. And do regular linear convolution, and you'll find out that linear convolution ends up with a finite duration signal, but it's longer. In fact, it will be length 7. So you convolve a length 4 with a length 4 with zeros before and zeros after. Do the linear convolution, you'll get a length 7 output. So that's a key distinction between linear convolution and circular convolution. Okay, so let's go to the next slide. So hopefully now you can envision circular convolution. I would encourage you to do some practice on that. I will post some homework problems on that. Let's look at another result. So remember that we are now, in the scenario that we're talking about, so far we've set up that we kind of have this view that we have, the physical reality is we take a chunk of signal and we take a DFT of it. Then if we take an inverse DFT, remember we said that really to capture the essence of the mathematical machinery behind it, we really need to think about that inverse DFT as resulting to be a periodic signal. So here's the viewpoint that you should just train yourself to think about. As soon as you grab a chunk of signal data and you're going to think about doing DFT processing on it, you should immediately think, I should treat that chunk as one cycle of a periodic signal. And then we transform it over into the DFT, and remember, we really only compute n DFT points, but since we view those as points on a DTFT, we know that there are really mathematically lurking there a periodic underlying DTFT, and therefore we should view the resulting DFT samples as just one cycle of what really is there mathematically. So here's the bottom line, and I haven't really started discussing the 2 results here, I'm just setting it up. When you're thinking DFTs, even though physically we're going from a chunk of n to a chunk of n, think each chunk of n on each domain is really periodic. So I grab a chunk of n in the time domain, think of it as being periodically extended. I then compute n DFT points, think of those as being periodically extended. So then we can think of the DFT, even though we don't really physically do it that way, we should really train ourselves in the back of our mind to think periodic thing into periodic thing, and then back again. And as soon as you realize that what you're doing is just basically mapping a periodic thing into a periodic thing, you suddenly can gain insight into the behavior that you wouldn't ordinarily expect. So remember that the DFT and the IDFT have almost exactly the same structure. Remember when we viewed them as a matrix, the matrix for the IDFT is basically the complex conjugate of the matrix for the DFT. So they're basically the same process. We would expect dual results to be very, very similar. So we just saw that a product in the frequency domain, so a product of DFTs, gave us a circular convolution in the time domain. Now, what would you think if we did a product in the time domain of two chunks? Think periodic. So I'm multiplying these two periodic things. They have the same period, period of capital N. What's going to happen when I transform that product over into the DFT domain? Well, since the machinery is pretty much the same as inverse DFTing a product, I should expect almost exactly the same thing. I get a 1 over n out in front just because of that pesky 1 over n in the definition of the inverse DFT. But what it says is that the product of two chunks of discrete time signal, take a DFT of them, the resulting DFT is the circular convolution of their individual DFTs. So this is a dual of the convolution properties for DFTs, but it's also the DFT version of time multiplication for DTFTs and for CTFTs. And then the second result on this page is Parseval's theorem. All of the transforms that we've seen preserve energy in some fashion. This is a very handy result. If we take two signals and we're accounting for the possibility of them being complex, so we're allowed to take the complex conjugate there, or we should take the complex conjugate there to get this result to work. And we take the product of x1 times x2 conjugate, add up all those results, that will be equal to doing the same operation in the DFT domain, conjugating 1, adding them all up. The only thing is we need to account for the 1 over n, which is kind of the nuisance constant out in front of the IDFT. Special case, if x1 and x2 are equal to each other. So when that is the case, then x1 and x2 become equal to each other. So this is just x1 times its complex conjugate, which boils down to magnitude squared. And same thing over here, boils down to magnitude squared. And so this is the sum of magnitude squares in the time domain equals sum of magnitude squares in the frequency domain. So that's also maintained with the DFT. So we have this kind of Parseval's theorem for a lot of things. CTFT, Fourier series, DTFT. In fact, it's kind of a goal of any signal transform that you're interested in applying. Parseval's theorem is kind of a key result. And if you go on to graduate school or to even more advanced senior level DSP classes, this idea of Parseval's theorem is extremely important and pretty widespread. Okay, last slide. This set of notes, just some quick and dirty results here. Just what happens if we take the complex conjugate of a signal. So we've got a signal x of n, and it's got a DFT that's just x of k. If I have the complex conjugate of that and I take its DFT, it's the conjugate, but it is also reversed, but with mod n. The best way, again, that I think to think about that is to think about conjugating it, periodize it, and then flip the periodized version. Or equivalently, we can view it this way. So we're just essentially starting out at n. So we start out at the end of it, in fact, 1 point beyond the end of it. And as k goes from 0 up to n minus 1, we work our way backwards through the elements. So that's one way to think about it. And then we have a related result which is the IDFT of the complex conjugate. So this was conjugating in the time domain. This is conjugating in the frequency domain. So again, we have an x of n with an x of k, and we ask what happens if I take the conjugate in the frequency domain. So I conjugate my DFT and then I transform back. What effect does it have? And it conjugates and periodized flip. A lot of confusing subtle points in here. Will require you doing some practice on these, and I'll post some problems for you to work on when you get to this point. All right, thanks. We'll see you in the next set of notes.